This project is a shower heater controller built using Verilog. It controls three things: the heating element, the pump speed, and the flow diverter, all based on instructions sent to it every clock cycle. The entire system runs on a 4-bit instruction format, meaning every command is just 4-bit digits. There are 5 modules in total. I will explain the overall architecture and the instruction decoder. Think of the decoder as the brain. It reads every instruction and decides what mode the system is in and what thermostat temperature to target. The instruction is 4 bits: bit 3, bit 2, bit 1, and bit 0. So bit 3 is equal to opcode. If it is 0, this is config instruction. If it is 1, this carries a thermostat temperature value. Bit 2 is the thermostat change flag or TCF, only active when bit 3 is 0. If TCF is 1, it warns the system that the next instruction will carry a new temperature setting. Bits 2, or mode or temperature, where bit 3 is 0, these 2 bits select the operating mode. When bit 3 is 1, they become a part of the 3-bit thermostat value. So the system always needs 2 cycles to change temperature. First cycle raises the TCF flag as a warning. Second cycle delivers the actual value. So the decoder has 5 inputs: clock, reset, power bit, and the 4-bit instruction. It outputs 2 registers: mode 2-bit and thermostat 3-bit. So register pending thermo. This is the internal handshake flag. It gets set to 1 when TCF is equal to 1. Is detected and cleared back to 0 after the thermostat value is successfully lodged. Always passage clock. The entire decoder is clocked. It only acts on the rising edge of the clock. If reset, on reset everything goes to 0. Mode 00, standby. Thermostat is equal to 000 or 38 degrees Celsius, and pending thermo is equal to 0. Else, if the system is powered off, the decoder freezes. No latching happens and pending thermo is cleared, so a half-finished handshake cannot accidentally fire when power returns. If instruction 3, this is config instruction, the mode is always updated from bits. Then it checks bit 2. If instruction 2 is equal to 0, TCF is equal to 0. Pending thermo is cleared. Normal operation, no thermostat change coming. If instruction 2 is 1, TCF is equal to 1. Pending thermo is set to 1. The decoder is now armed and waiting for the thermostat value on the next cycle. If instruction 3 is equal to 1, thermostat instruction, it checks pending thermo. If it is 1, the handshake is valid. Thermostat is latched from bits 3, and pending thermos is cleared. If pending thermo is 0, the instruction is silently ignored. No stray temperature change allowed. So mode encoding summary: 00 is standby, pump off or heater off. 01 is warm, pump low, heater on the thermostat demand. 10 is hot, pump medium, heater on the thermostat demand. 11 is equal to boost, pump high, heater on thermostat demand.
What does the ALU do? The ALU is the temperature decision maker. It takes the 3-bit thermostat register from the decoder and converts it into an actual temperature threshold. Then it compares that threshold against the real water temperature and decides whether the heater should be cold to run. It uses a technique called hysteresis to prevent the heater from switching on and off too rapidly. The ALU has 5 inputs: clock, reset, power bit, 3-bit thermostat, and an 8-bit current temp. Its output is a single-bit thermocall. a 6-bit internal register. We need 6-bit because the highest temperature is 55 Celsius, which fits in 6 bits. In this line, threshold lookup table. This is a combinational block, no clot. It instantly converts the 3-bit thermostat code to temperature in degrees Celsius. From 00 is equivalent to 38 Celsius, and 001 is equals to 40 Celsius, 010 is equals to 42 Celsius, 011 is equals to 44 Celsius, 100 is equals to 46 Celsius, and 101 is equals to 48 Celsius, 110 is equals to 51 Celsius, and 111 is equals to 55 Celsius. And the default threshold is 38 Celsius. In this line, hysteresis comparison. This clocked to prevent glitches. It runs every clock cycle when the system is on. And here, power bit is not equal. System is off. Thermocol is forced to 0 immediately. No heating when power is off. And in this line, current temp is less than threshold minus 2. The water is too cold. Is set to 1, demanding heat. For example, if the thermostat 44 Celsius, this fire when temp fails to 42 Celsius or below. Else if current temp is greater than threshold plus 1. The water is warm enough. Thermocol is set to 0, stopping the heat demand using the same example. This fires when temp reaches 45 Celsius or above. Else, hysteresis band, no change. If the temperature is between 43 Celsius and 44 Celsius in the example, thermocol holds its previous value. This dead zone prevents rapid toggling known as chatter. In summary, the ALU turns a thermostat code into a real temperature, then produces a single yes or no signal, thermocol, that tells the controller whether to heat the water.
Our two modules handle the physical output side of the system. The heater delay module is a safer timer. After the heater turns off, it enforces a mandatory rest period before the heater can turn on again. This prevents thermal shock and element damage. The control unit is the output driver. It takes the mode, the thermocol signal, and the other delay status, and decides exactly what the heater pump and diverter should be doing. Okay, let's proceed to heater delay module. This module has one input called start delay and one output called delay active. Delay off equals to 15. The heater must stay off for 15 clock cycle after shutting down. Rig ratio 30, 4-bit counter. 4 bits can count to 15, which exactly the delay needed, not one bit wasted. If start delay, when a start delay pulse arrive, delay active goes high and the counter resets to 0. The timer has begun. Else, if delay active while the delay is running, the counter is increment each clock cycle. If counter is a less than of delay, it means keep counting. Else, counter has reached 15, delay active goes low. Counter resets to 0. The heater is now allowed to turn on again. Now let's proceed to control unit module. The controller receives power bit, heater enable mode, thermocol, delay active, current temp, diverter enable. It derive start start delay, heater, pump speed, and flow diverter. Rig heater prev stores the previous heater state to so that the controller can detect when the heater transitions from on to off and trigger the delay timer at the exact moment. Start delay is defaulted to 0 every cycle. It is only pulse high for one cycle when needed, preventing the timer from being re-triggered. If power is off, the output are immediately forced to 0. Heater off, pump off, diverter closed, delay pulse cleared. Then standby, um, pump speed is set to 00 or off. It is the heater was on before this thermocol. Oh, before this mode was selected, it is turned off and start delay pulse into protected element. Thermocol is don't care here. Mode overrides it. Then in warm, pump speed equals to 01 or low. If thermocol equals to 1 and delay active equals to 0, the heater turns on. If thermocol is equals to 0, heater is on. The heater turns off and the start delay is pulsed. Now in hot, pump speed equals to 0 or medium. Same heater logic as warm, but pump run faster. Then sa boost, speed equals to 11 or high. Same logic sa sa warm, maximum water flow, fastest heating. Then flow diverter less than or equal to diverter enable. This single line outside the mode switch, the diverter is completely independent of heating mode. Even in standby, if diverter is equals to 1 or diverter enable equals to 1, the diverter opens.
The shower control tab is where all our module is being connected instantaneously, where the input is the clock, reset, 4-bit, a 4-bit instruction, 8-bit current temp, and the diverter enabled, and it outputs the heater, 2-bit pump speed, and flow diverter. And here are the worded, the 2-bit mode, to 3-bit thermostat, thermocol, delay active, and delay and the start delay. And here are the module, the shower instruction decoder D, shower ALUA, shower
heater delay R, and the shower control unit C. So why are we doing this? So that we can directly access the report and give the input value on each of their modules so that it won't get mixed to the other modules. Now on the second part is the module as shower stimulus generator where our value input is getting generated here. So how it works when reset is 1 and power is off, then all our system is turned off. And if the reset is 0 and power bit is 1, then the system operate continually or it operates normally. So how it works, if in the instruction is 000, is this is a standby mode. So the current temperature is 20 degree, and it sends it instruction bit to update it. And on the second part is the warm or the warm mode, which is the 0001, which is it increment the current temperature twice. It increment the temperature one time, one at a time. And on the third mode is the hot, which is 0010, which it increment twice as much as the second one. So here, and the third type, in the fourth, and the last one is the boost or 0011, which it will increment the current temp third time as third times as much as the second one. And after that, it will power off the bit and it finishes the, the stimulation. So this is the shower control test bench where all of our GTK wire output we're going to display, and here is how we call them. So it will give the value and will display it on the wires. Now on the GTK wave, the clock sends the clock only updates the register every rising edge of the clock, and so on and so forth. So at the first one we're going to discuss is the reset. If the reset is 1, all of the system is off. The system is off, and then when the reset is 0, then the system is working properly. Now question, why is this part is not yet been updated? So we set it to only update the current temperature after the 16-bit is done. Now on the first one is the instruction. If the instruction is 000, then it is on standby mode. So as I've said so earlier, it will do nothing and it will not increment or add something to the current temperature. That's why it's flatline. Then on the second one, instruction is 0001. This pump speed is being active. The pump speed is being updated to 01. So it will increment the current speed, the current temperature, 1 degree Celsius at a time. So on the second part, And the second part is the warm. The warm. So if the instruction is 0010, then the pump speed is 10. So the current temperature will increment twice twice two times as the 2 times degrees Celsius at two times at the time. Just like I explained earlier. And and for the last one, if instruction is 0011 and the pump is being updated to 11, so the current temperature will get incremented three times three times to its degree Celsius, and, and so on. And after that, when the power is off, then all the system is turned off. And that's all for now. And thank you.